I will be talking about some of the work that we are doing, and it has to do a lot with stuff that breaks, as the title suggests. So we have a lab where we get to break things, and that in and of itself is a lot of fun. So we get to play around and bang on things until they fall apart. But we do that because there's a realization that it would be really useful to know the underlying mechanisms of why things are breaking. And it is a fact that in life, as soon as you build something, it starts to deteriorate, to degrade. And depending on the how quickly something breaks, we call it degradation, or we call it a fault if it happens really quickly. But fundamentally, what we really would like to know is why is that happening, right? What are the underlying mechanisms? And it doesn't really matter whether it's a biological system where, as we all know, cells start to age over time and eventually give up, or chemical systems, where you see some changes with time and with certain stressors, or electrical systems where you have, say, in power semiconductors or so, things are just starting to diffuse and you have tunneling effects and things are not working as expected anymore. Or, of course, in mechanical systems that we perhaps are most comfortable with, where you have effects such as friction or ablation or abrasion or also diffusion that change things and lead to some undesired effects where ultimately you lose the desired functionality. So you design things to last a certain amount of time, but sometimes it does not, at least to the designed life. And what we would like to do is to do that earlier. So now that we have come to grips with that stuff does break, what are we going to do about it, right? And the answer may be, well, nothing. We just let it break, right? If it's not important, if it's cheap, you just let it go. But in many cases, you want to know when it is breaking, and or you want to prevent it. And a common practice, for example, in the aviation industry, is to do some preventive maintenance. So after X cycles, after 2,500 cycles or so, you replace a certain engine part. And it doesn't really matter whether it's worn or not. You have to replace it to make sure that the part does not break. And that is expensive, but it keeps you on the safe side. What you also could do is to put on a system that monitors the performance over time and that tells you that something is going downhill. And then you can turn it off before you have some secondary damage or before it cascades into some catastrophic kind of event that is going to cost you a lot of money or that impacts the safety of operations. And if you can, and so that then leads to the condition-based assessment, where you are tracking things as they are being used. And as a next step, you're also then trying to predict at what point the system will reach some functional limit. And that is called prognostics, and that's what we have been working on. The promise of that is that you can perform maintenance only when it is needed. So you're not exchanging the part that really is brand new and that you could use for another few thousand cycles. You do not have to change the oil in your engine every 2,500 miles or 5,000 miles. You change it when it is needed, and so that has obvious implications for cost, and so that's why industry is very much interested in that, and it also has implications on safety, because you can ensure that you have safe operations, and that is something that astronauts, for example, are interested in, right? So they are. It's good to have the a priori statistics on the space shuttle, for example, that you have a 2 in 50 or 60 chance of surviving, but once you're in the beast, you want to know, is this the one that's going to make it or not? So how do you go about predicting stuff, right? So There's different methods, and there are different industries that have been in the business of predicting. You can go to a fortune teller and try your luck there. That may, as a scientist, not be very satisfying because perhaps the repeatability or the underlying scientific implications are not as clear. But we see in other industries that it is being done also, right? So even in the economy, any retailer needs to know where is the fashion trend going so that they can buy stuff a season or start manufacturing things 2 seasons ahead of time. And so they need to have some sort of sense to understand where are things going. It's also being done or tried in predicting stock performance, which sometimes works better than other times. And when I teach classes in AI, I always have students do a project, and I tell them, don't do stock performance prediction because it's not going to work. And they don't take my advice, and it doesn't work. Anyhow, but you can also do that for equipment, for industrial equipment, for things, for engineering systems. And that's what we are in the business of doing. And so for prognostics, you need a few ingredients. What you need to do is to have some sort of understanding of how your system works. And that can be done in a couple of different ways. Either you try to understand the physics, and you go back and do first principles modeling, where you encapsulate the performance or the behavior of a system using physical equations. And you also need to understand something about the degradation mechanisms and also encapsulate those with physics equations. And then you can, once you get sensor feedback, you can essentially make a comparison. And if the system is starting to deteriorate, you can do some hypothesis test. You know which of the failure mechanisms is currently dominant, and you go with that one. And then you can extrapolate that out into the future and assess what is your remaining life. Right? So that's done here on this slide, where you have some measure of health on the y-axis and time on the x-axis, and you see that the health, which is that red line, is changing in some nonlinear fashion, and that is a very typical line or behavior of health that you can see. And you measure a few things, which is a green wiggly line, and then you start predicting things whenever it's convenient or whenever you need it, right? And the idea is that you have a good enough understanding of both the system so that you can predict, and the blue curves here are supposed to be PDFs that give you also a measure of uncertainty of how sure you are. And as you are getting closer to the end of life, your PDF is supposed to shrink so that you are more and more certain about things happening. You also need to know something about future usage. Right? If you are stressing your component more than you have in the past, you shouldn't expect that it will last quite as long. And so that's important as well. But you can't be completely sure, in particular about future usage. You can't be completely sure about your sensor measurement. You can't even be sure about your model, right? So your model is only some sort of rough approximation of reality. Model, of course, is made up of model structure and model parameters. Each one is fraught with uncertainty. And so you have to put all that together and have a mechanism that does that such that your uncertainty bounds in the end are not unreasonably large. So, for example, if you predict that your system will fail in 3 days, plus minus 3 days, then your prediction isn't very useful, right? So you have to figure out a way to do that in a rigorous mathematical way. Your modeling, of course, could also be done using data-driven methods. So that's where AI or machine learning and all that, those methods that many of us are familiar with come into play. For that, you would need to collect actually a number of instances of how your system is degrading, and all the way up to failure. So you need to have these time series so that you can learn over that and build a representation of how the system is degrading. You also need to have an understanding of what your failure threshold is. We like to think of the failure is when things blow up, right? But that's not necessarily useful, because if you're trying to use a method like that, you need to be able to quantify how far away am I from that event. And so what is more useful is to go with for example, with some requirements that you can quantify, or some functional specs or something like that. And if you're falling outside of those bounds, then you can determine how far away am I from that event. So, and of course, there's a bunch of mathematical methods. Since I knew I only had 10 minutes, I left out the other 63 slides that have all the gory equations. But one method that is particularly useful in this context is a particle filter, which is a method that does not require to assume Gaussian distributions of uncertainty, for example. So that's what we have used very successfully in this context. And it's not all just theory, right? So we have tried it out. And these are some of the components and systems that we have played with in the lab. So these are electromechanical actuators, which could be used on an aircraft, for example. Electrochemical storage, such as batteries. They are very useful for testing out your methods, because they are a component that you can degrade quickly, cheaply, repeatedly, and it has some interesting degradation phenomena because it is also impacted by temperature and by load and all kind of thing. Electronics, we have played around with power semiconductors, IGBTs, MOSFETs, etc. Very different animal. So for each of those components, you would have to measure completely different things, and you would have to model it in very different manners as well. Valves and pumps, what you see here is a pump on the propellant loading of a rocket, in this case it was for a space shuttle, but similar valves exist for other rockets as well. And as you are loading the rocket, you really want to make sure that the valve works then, right? Because if it doesn't, you can't load it. You have to scrap the launch. It's very expensive, and a lot of people are very unhappy. Composite materials, they really are in vogue now, but they are very difficult to understand because they are not very homogeneous, unlike metallic structures. So here you have the matrix, you have the fiber, you have all kinds of weird damage phenomena, such as cracks and delaminations and fiber breakage, and each damage mode is dominant at a different time. Solid rocket motor casings. So we have typically you have very few sensors on space-going systems, because every gram counts as weight, and it's expensive. So you have just a couple of sensors, and you have to reason over is there some valve clogging which could lead to some damage? Is there some sort of crack in your casing which expands rapidly, and you have to perform your calculations faster, because you have to give the astronauts lead time to eject ahead of the pressure wave so that they're surviving, right? So, and you really can't afford to have any false positives, which are very embarrassing, right? So you eject, and there goes your asset with a few $100 million into space. You really don't want to have false positives. At least the astronauts don't want to have any, false negatives. Very unpopular. Rovers, UAVs. This was actually UAVs was our first application where we integrated and tested our prognostic algorithms. This is an electric UAV. Electric aviation is becoming very popular. similar to or catching up with terrestrial electric transportation. But if you're in the air, you really want to make sure that you have enough juice left to land safely. And of course, your remaining charge is impacted by headwinds and all kinds of other disturbances. Wind turbines, also biomass, so we have deployed the same kind of techniques also on organic materials. So, very different animals, but the same kind of process applies here as well. Thank you very much. Does anybody have any questions?
As Jessica's setting up, exactly. We can take a question or two while Jessica's setting up, if anyone has a questions for Kai.
So the question was, how do you use techniques like that on a system where you don't have a whole lot of experience-based data, such as on a satellite? And it's true. Same for rockets. We cannot afford to blow up 100 rockets just because we want to have some trajectories to test out different kinds of fault modes. So the way you typically do it is you have a maturation process of techniques where you are successively testing, verifying and validating your techniques. Right? So you start out with something very theoretic. Then you have some simulations, perhaps. You test whether your crude algorithms are working. Then you go into lab tests. You test it out on at the component level, which is still affordable. You may have some old data as well, and so there's of course always a delta between what you're testing it on and the real thing. But successively, you're getting more and more confident that the technique does what it's supposed to do. And in the end, you're still not going to have 100% certainty that it really will do what you do. And but that's also a fact of life, that you need to be able to acknowledge that you will never be completely sure.